A function f defined from matrix space x to matrix space y is said to be bounded if the range, that is f of x, is bounded subset of x. Sorry, bounded subset of y. So when we can say a function which is bounded if the range of this function will be bounded. For example, if you have a function f from R to close interval 0, 1, f of x is equal to x. If I define like this, is it possible to define like this function? Not possible. Can you give me another example of a bounded function? So I can say that f, which is function from R to R, f of x is equal to sin x for every x belongs to R. Then we know that the range of this function f is closed interval 0, 1. Sorry, minus 1 to 1. Closed interval minus 1 to 1. So therefore this f of R under this map, it is closed interval minus 1 to 1, which is bounded. Therefore this function f is bounded. Now the question is, under the continuous map, boundedness is preserved. That means x is bounded. Can we say that the f of x is also bounded? So that is actually a corollary of that compact set result. So this we have is, if f is a continuous function on a real value, so continuous real valued function defined on closed interval AB, then prove that f is bounded. Probably you have used this result many a times in your previous study. For example, when you are proving your RMBT theorem, that is Rolle's mean value theorem. In the first statement, you are assuming that to prove that statement, RMBT means Rolle's mean value theorem. In that you have stated your f is continuous on a closed interval AB. And if your f is differentiable on open interval AB, and f of A is equal to f of B, and there exists C belongs to AB such that f dash of C equal to 0. So to prove this statement, you have used this result many a times, because first statement is saying that f is continuous on AB, then we know that this f dash of C is 0. It's possible when it will have a slope which is parallel to x-axis is there. So it is possible when the graph of the function is of this type. And here it is possible if this function is bounded, otherwise it is not possible. So that values is local maxima and minima is there. So this value C is either local maximum value or local minimum value, and that is gives the quantity that the function has to be bounded function. And we have used this result which we are discussing right now, and afterwards what I am taking. Both these results you have used so many times, but here we are discussing the proof of this result. So what is the proof? Since f is defined on closed interval AB, we note that this closed interval AB is a closed and bounded subset of R. Therefore, this closed interval AB is compact, and f is continuous, so therefore f of AB is compact. Since f of AB is compact, it is totally bounded. Since it is totally bounded, it will be bounded. So therefore f of AB is bounded. Since this is bounded, f is bounded. Ultimately, what is says that if you have considered any closed and open subset of R, then any function which is defined over closed and open subset of R, then that function is always bounded function. That we can say from this. Not only we can say that it is bounded, but the next result tells you that in this interval it attains its bound. That is exactly in the proof of Rolle's mean value theorem you have used, that the C lies inside this interval AB, and this C point is a local minima or local maxima. And why it gives you guarantee that it is always lies in this interval? Due to this results which we are going to discuss next. So this is the theorem actually that I am writing. If f is continuous, real value function on a compact matrix space, X, then f is bounded and attains its bound. So it will attain its bound as well as it is bounded function. So it gives you lots of more than the boundedness. That means whatever the maximum and the minimum value of that function, because now a function is a real valued function. A function is from X to R, and X is a compact matrix space. So you can talk about the maximum value and the minimum value, and that value will be lies inside this for some values of X is possible. Why it is so? Because of this compactness is there, that's why we can have that. So let us talk the proof of this. So first of all, here we have a function f which is from X to R, is continuous, and X is compact. And we have seen that continuous image of a compact metric space is always compact, so therefore f of x is compact. Compact subset of R. And in R, closed and bounded is equivalent to a complex fact. So I can say that f of x is closed plus bounded. Now bounded gives you bounded, f of x is bounded, that means it has a maximum and the minimum. So this will gives you boundedness, therefore f is bounded. Let us consider that the LUB, let's say this capital M is the LUB of f of x. X belongs to x. And small m is the GLB of this. Since x is closed, this LUB and GLB must lies inside. So since x is closed, this capital M and small m must belong to f of x. In fact, f of x is closed, that's why we can say this. Fx is closed. F of x is closed, we can have this. Therefore, there exists some point x and y in x such that fx will be capital M and fy will be small. So that means we can say that f attains its maximum at x belongs to x and f attains its minimum at y belongs to x. So this theorem tells you two things, or here we have used one thing, that any set closed, any subset of R which is a closed, then LUB and GLB lies in that set. And the above theorem is not true for, so if I drop this condition from this, that means if I drop this compactness from this theorem, then the result is not true. Can you have any example for that? So consider, define this function f from open interval 0, 1 to R as f of x is equal to 1 by x for every x belongs to open interval 0. And obviously this function is continuous on the any point in between 0 and 1, but it is not bounded on open interval 0. Okay, so we can say that because why this is there, because this set we have here, it is not compact. If it was compact, then definitely we can say that it is a bounded function. This is not a bounded function. So we know that f is continuous open interval 0, 1, but f is not bounded. So this is the first example. The second example, can you have any example which has LUB and GLB, but it will never attained by this function? Yeah, we can have this such type of example. That means if you have defined a function open interval 0, 1 to R as f of x is equal to x for every x belongs to closed interval 0, 1, then this function is bounded function. But this function does not attain its bound because LUB of this function is 1 and the LUB is least upper bound is 1 and GLB is 0. And it will never attain by any value of this closed interval 0, 1 because the function is this. So we can note here f is bounded and continuous on open interval 0, 1, but LUB of this f of x belongs to open interval 0, 1, we know that it is 1, and GLB least greatest lower bound, that is f of x is 0. But the function never attained this point or this value, never attained this value. That means there does not exist x and y in this open interval 0, 1 such that f of x is equal to 0 and f of y is 1. So there is no point in this interval which having this least upper bound and greatest lower bound. Okay. The next result, we can take it as a corollary of this. If you have a function, so see, any function which is defined over the closed interval AB to R, from this result, which is, we can take that, or we can say that a function, if it is continuous, then it is always bounded. Based on this, there are many examples asked in the NET examination, many times, so many times. Because, see, if I can have such examples, so whether if you want to say that set is not on this, sorry, not on this one, but let's discuss the next example, or the next theorem. If f is 1, 1, continuous function from compact matrix space X onto matrix space Y, then prove that F inverse is continuous from y to x. So ultimately what it says that if you have a function which is 1 1 and onto, which is 1 1 and onto, and which defines on compact matrix space, then it is homeomorphism. See, any map which is x to y, which is 1 1 onto plus x is compact, then this will implies that it is a homeomorphic function. This is very strong results actually you have. So with this result, I can also have add one property which we are discussing in the previous lecture, or sorry, in the previous discussion, that if x is compact implies f of x is compact. So that means compactness is preserved, conversion sequence is preserved. Here now, due to this result, if f is 1 1 and onto and if your x is compact, then it will also preserve the openness and closeness. That means if x is closed, then implies f of x is closed under the compactness, under the compact matrix space. So this is very strong results you have. Let us discuss the proof for this. So given that f from x to y is 1 1 and onto, therefore if I define a g is equal to f inverse is exist, I want to prove that this g is or f inverse is continuous. We shall prove that g is continuous. So ultimately I have to show that inverse image of open set is open, or I can prove that inverse image of a closed set is closed. Both the things is valid. So it is sufficient to prove that. F is closed in X implies G inverse of F is closed in Y. This is our objective. So I'll start with, for any closed set F in X. Start with this. And X is compact and F is a closed subset of X. So therefore, your F is compact. Because every closed subset of a compact matrix space is compact. Due to this, F is compact. Since F is compact and small f is continuous, f of f is compact. Since it is a compact, I can say that f inverse of f is compact. So therefore, G inverse of f is compact. Therefore, G inverse of f is closed, because any subset or any set which is compact implies it is a closed set. So therefore, this G inverse of f is closed, and therefore G is continuous from y to x, and hence your function f is homeomorphic. So if you have any function which is defined from x to y and which is continuous 1 1 on 2 and your x is compact, then this is automatically homeomorphism. See, the compactness is essential here. If you drop this condition of compactness, then your result will not be true. Then you cannot achieve this result. So for that, I am giving you note here that compactness is essential in above theorem. It's very important. If you can drop that condition, will not be true. For example, if I consider this x as open interval 0 close 1, or sorry, close 0 open 1 with usual metric. On R, with usual metric. With usual metric, this is that. Define a function f from x to r as f of x is equal to e power 2 times 2 pi ix. That is actually 2 cos 2 pi x plus I sine 2 pi x. I can say this is a subset of R square. Okay, this will be the subset of R square. So what is this map is actually? This map is gives you this. It's a map from this interval to, so it is every map, every point on this interval 2 onto this circle. So this points, that is cos 2 pi x sine 2 pi x. For example, the image of 0 is 1 comma 0. We have here. Okay, so the image of this point 0 is 1 comma 0 and so on. Every point is mapped to this, except you have one point is dropped from this. Okay, so this is gives you, and one can note that this function is actually continuous function, which gives you every point on this which maps on this circle. So this function is continuous, which is actually also 1 1 and onto which we also can prove. One can prove that. So we note here f is 1 1 onto and continuous. But f inverse is not continuous. That we are going to prove here. Right? So our claim is f inverse is not continuous at the point f of 0. So consider the sequence xn, which is 1 minus 1 by n. So this will imply f of xn, which is e power 2 pi I into 1 minus 1 by n. And we know that e power cos 2 pi I will be 1. So it is e power 2 pi I by n minus n. Where is this converge? This will converge to 1 as n tends to infinity. Because 1 upon n is there, so it will converge to 0. This will converge to 1 as n tends to infinity. But f of 0, we know it is 1. So therefore, I can say that f of xn is converged to 1 as n tends to infinity. So what we have here, f of xn is converged to f of 1 as n converges to, sorry, f of 0 as n converges to infinity. This will not implies that f inverse of f of xn will converge to f inverse of f of 0. Because what is f inverse of f of n? This is actually xn. This is xn. And this xn is 1 upon 1 minus n. And this will converge to 1 according to this. But 1 is not contained in this x. 1 is not containing in x. Because the x we have defined is close 0 open 1. So therefore, this f inverse is not continuous at f of 0. So we can say that the compactness is essential for this. Okay. So now I will stop for today here. If you have any question, you can ask.